Hello everyone, my name is Yuan, and I'll be talking about the detection of black hole-driven turbulence in the centers of galaxy clusters. Galaxy clusters are filled with hot ionized plasma called the intercluster medium, or the ICM. We can see this ICM using X-ray telescopes because the ICM is emitting a lot of X-ray photons via Bremsstrahlung radiation and is therefore cooling. In the centers of many relaxed galaxy clusters, we can see these X-ray bubbles or cavities filled with radio-emitting plasma. These cavities are created by the jets coming from the supermassive black holes. And somehow this feedback energy goes into heating up the intercluster medium to offset the radiative cooling loss. However, how this coupling happens is unclear, and it's hard to know the kinematics of the hot gas due to the limited spatial and spectral resolutions of X-ray telescopes. Luckily, the centers of many galaxy clusters are multi-phase, with cold filamentary structures that extend to tens of kiloparsecs. What I'm showing you here is an H-alpha image overlaid on top of the X-ray image of the central region of a nearby galaxy cluster called the Perseus Cluster. H-alpha probes gas with temperatures around 10 to the 4th Kelvin and can be observed with ground-based optical telescopes. Now, instead of showing the H-alpha flux, I'm showing you the line of sight velocities of the filaments. As you can see, the motions of the filaments appear random, but are we seeing turbulence here? To find out, I computed the velocity structure function of the Perseus filaments, shown on the right-hand side. A velocity structure function simply relates the separation of pairs of pixels and the mean velocity difference at those separations. As you can see, the velocity structure function shows a beautiful parallel on small scales, which is what you would expect from a turbulent flow where big whirls are turning into little whirls. The velocity structure function also reviews where the energy cascade starts, or the scale at which the energy is injected into the system. And this scale, at about 10 kiloparsec, happens to be the sizes of these X-ray bubbles highlighted with the radial contours on the left-hand side. So are we seeing turbulence driven by the supermassive black hole? In case you're not convinced, I've also drawn a circle to divide the filaments into inner filaments and outer filaments. The inner filaments of Perseus follow a structure function shown in red, and you see a more prominent bump at about 10 kiloparsec. The outer filaments follow the structure function shown in green, and they don't seem to care about the inner bubbles, which makes a lot of sense. Instead, the outer filaments reveal a driving scale at about 20 kiloparsec, which is exactly the size of this older bubble. So it's possible that the outer filaments in Perseus mostly follow turbulence driven by a previous Aegean outburst. We have also looked at another nearby galaxy cluster, Abell 2597, and we saw the exact same story. The inner filaments follow turbulence driven by the inner bubbles. The outer filaments follow turbulence driven by the older bubbles. And lastly, we also looked at M87 in the center of the Virgo cluster. And again, we see beautiful parallel on small scales in the velocity structure function. And the inferred driving scale is again the size of the bubbles and also the size of this jet. So in all three galaxy clusters we have looked at, we find that the motions of the filaments are indeed turbulent, and there is clear evidence that the turbulence is driven by the activities of the supermassive black holes. So the results tell us a lot about how black hole feedback energy is coupled to the surrounding gas. It also demonstrates that we can use cold gas as a tracer of the hot plasma to study things that cannot be done with X-ray observations. Thank you.